to other spaces as well. So we restrict harmonic polynomials to a sphere, and homogeneous harmonic polynomials of degree k, we're going to call them spherical harmonics of degree k. So we're going to work with spherical harmonics. What do we know about spherical harmonics? What are the main properties that are going to be interesting for us? Well, first, it's a finite dimensional space, clearly. The dimension can be explicitly found. So it's the dimension. We're gonna denote it hk. I don't put the letter d here, although of course it depends on d. So just through the whole paper, we're gonna work in the d-dimensional space, d-1 dimensional unit sphere. Everything is gonna happen here unless it's specified differently. So on this space of polynomials, we can actually define a scalar product in a very natural way as an integral of the product of two functions. The measure is going to be normalized, so we're going to use the fact that the measure of the whole sphere is 1. Just going to be convenient for us. Okay, so we have this finite dimensional vector space. There's a natural scalar product defined in this finite dimensional vector space. Well, surely we can get an orthonormal basis there. So let's do that. Let's start with some orthonormal basis. And let's define the following map. So this map phi k is going to be crucial for our construction. So for any point on the sphere, we're going to define the values of the orthonormal basis at this point, and we're going to normalize it by the square root of the dimension of the space of spherical harmonics of degree k. So this is going to be our map. We're going to work with that. So what kind of map is that? What can we say about this map? And the main property is that the scalar product of images under this map actually depends only on the scalar product of the arguments. So the scalar product does not depend on the choice of the orthonormal basis and does not depend on what particular points you choose. Just depends on the distance between these 2 points. I'm sort of wiping it under the rug. I don't want to prove it, but the typical way to prove it is there are several ways how to do that. The bigger way is to use representation theory, because these spherical harmonics are connected to unitary representations of the symmetries of the sphere. So that's one way to explain why it does not depend on anything else. And the other way probably is to work with linear functionals and to use the Riesz theorem. So it's one more approach as well. Well, what can we conclude from here? So if this does depend only on the distance between 2 points, then switching x and y, we can see that the number must be real. So that's a real number, actually. On the other hand, if you substitute x and x and use the fact that this is an orthonormal basis, then you can actually conclude that phi k of x times phi k of x is equal to 1. So all of them are real. This is equal to 1. Well, as a matter of fact, it's a mapping from a sphere to a sphere. And this is going to be a sphere in dimension hk. Okay, so that's kind of the main point. We're going to look at these mappings that map sphere in dimension d to sphere in dimension hk. All right. So this is what we're going to work with. Okay. So what is this product? We have already talked about the product as it doesn't depend on particular points, just depends on the scalar product between them. So it's in fact equal to the value of the Gegenbauer polynomial, which are zonal spherical functions associated with this harmonic space. So what are these polynomials? Let me define them, I guess. So we can define them recursively. These are normalized Gegenbauer polynomials because we have just talked about the value for x and x. So the value at 1 when x and x coincide should be equal to 1. So the polynomial of degree 0 is 1, the polynomial of degree 1 is t, and there is an explicit recursive equation where you can get all the polynomials of higher degrees starting from the first. Okay. As a small example, probably it makes sense to talk about the case of dimension 2. So their Gegenbauer polynomials are just Chebyshev polynomials of the first kind. And if you look at this map, then it's just a k cover of the circle. So all angles are multiplied by k essentially. So this is what the mapping does. We shouldn't think too much about this example because in this is the case where the mapping is actually surjective, which is not going to be the case for higher dimensions. So in higher dimensions, the sphere of dimension d-1 is going to be mapped to a certain subvariety of a sphere in a higher dimension. So it's going to be a little different. That's not the best. That's not the most representative example for what's happening here. What else? These mapping a sphere to a sphere in a higher dimension, they're somewhat similar to a fairly well-known trick, which is a tensor power trick. So if you want to use your mappings for showing some asymptotic bounds and such, then probably you would do well with the tensor power trick alone. You probably wouldn't have this, I would say, more refined mapping that this mapping to the spherical harmonics offers. All right. So this is the definition of a mapping that we're going to use, the mapping to the space of spherical harmonics. Can we extend it a little? So again, we talk about phi k mapped from dimension d to dimension hk, which is an explicit number depending on d and k, and all scalar products in after this mapping are the values of the Gegenbauer polynomials of the scalar products that we had initially. Well, we can actually extend it to all non-negative Gegenbauer expansions. So that's fairly clear how to do that. Let's write it down anyways. So if you have a polynomial that is a positive combination of certain Gegenbauers, so here coefficients are going to be positive, the sum of coefficients are equal to 0, so that we can ensure that p of 1 is equal to 1. So that it's still a mapping to the sphere. Then we can define an associated mapping phi p, which is comprised of the mappings for all degrees I1, I2, and so on through I. And this is pretty clear that this is a mapping from dimension d to dimension h, which is the sum of dimensions for harmonic spaces here. All right. And the value of the scalar product after the mapping is going to be the value of the polynomial at the initial scalar product. So here we have a really nice tool on our hands. We can take any polynomial we like with positive Gegenbauer expansions. With a positive Gegenbauer expansion, we can map using this polynomial to a sphere in a higher dimension, and then we can work with that. So we have one set on a sphere, we can map it to another set on a sphere in a higher dimension. So if we know something nice about the spherical set in a smaller dimension, then maybe we can get a nice set in a higher dimension. And vice versa. If we can say something about the spherical set in a higher dimension, maybe we can conclude something in a smaller dimension as well. So that's our tool, and I'll try to convince you that it's a useful tool. For the first convincing argument, I'm going to talk about packing bounds on this sphere. Well, standard sphere packing problem, right? Finding the maximal spherical code given the separation distance. So if you're given an angle, you may be asked about finding the maximal number of points such that all pairwise distances are at least this angle. And of course, the most famous example is the Kisin number problem. So when this angle is pi over 3, then it's the Kisin number problem. Alternatively, it can be formulated as the maximal number of non-overlapping spheres touching a given sphere of the same radius. And we have just literally a handful of answers to this problem. Dimension 2, dimension 3, 4, 8, and 24. So this is all what we know for the Kisin number problem. And there is an asymptotic bound due to Kapatansky and Revich. So that's one typical packing bound on the sphere. Okay, so we would like to apply our tool to packing bounds. So what are we going to do? First, we're going to reformulate it a little. Let's say we have a set from the interval from -1 to 1, and we'll have our spherical set with restricted scalar products. So all scalar products must lie in this set I, and this number MD of I will be the maximum size with restricted scalar products from the interval I. And of course, the packing bound that we were talking before can be formulated this way as well. You just take your interval from -1 to cosine theta, cosine of the angle. And in particular, for the Kisin number problem, it's going to be -1 to 1. Well, so let's try to apply the tool to that. So what are we going to get? In particular, this general approach should work. So let's say, and we take an arbitrary positive combination of the eigenvectors, and it defines a mapping from dimension D to this dimension H. Then all scalar products, if they were in the interval I, now belong to the interval P of I. So if we can say something about this packing bound in a higher dimension, then of course we can conclude something about our packing bound in a smaller dimension. Because from a restricted set in dimension D, we got a restricted set in the dimension H. So it's a fairly general approach. And let's try to get something out of it. So again, how's that supposed to work? We'll try to find a nice polynomial P so that we can use some packing bounds in a higher dimension. Whatever packing bound you like. So whatever packing bound you like from a higher dimension, we use it there, and then we get some information for the packing in a smaller dimension. Well, first, we can of course explain the method of the Delsart method using this approach, because a general packing bound like this works in all dimensions. If all our scalar products are from -1 to -c, then the number of points is no greater than 1 over c plus 1. So how do we get it? Well, you just look at the gram matrix of the set, and it should be at least 0. So 1 minus c times the number of points minus 1 should be at least 0, and this is where you get the bound from. Now, please note here that the bound doesn't depend on the dimension at all. Right? So it doesn't matter what d here is. It's a bound that depends only on the interval. So if we're able to map so that the interval is from -1 to some other negative number, we already get the bound. And this essentially is the Delsart method. So we have a non-negative linear combination of Gegenbauer polynomials. And the values of this Gegenbauer polynomials at our set of restricted distances belong to this interval from -1 to -c, then the number of points is never greater than 1 over c plus. How is that? Because we would use this mapping P, we would map to a higher dimension. And then we would use the Pekin bound in the higher dimension, but the Pekin bound doesn't depend on the dimension at all. So this dimension h that we would get from the polynomial P, it's irrelevant. You still get the same bound here. And this essentially is the linear programming bound. So essentially, this is a linear programming bound. Now, this is actually how all these nice results about Kisse numbers are obtained. If you find a very nice polynomial, you can prove that the Kisse number in dimension 8 is no greater than 240. The Kisse number in dimension 24 is no greater than 196,560. And if you work in this direction and you find the really right polynomial, you can prove the asymptotic bound of Kabatan's convention. So this all can be done using this inequality essentially. Well, but this is not all you can get via this tool. If you let's return back a little. So the reason why you can get a little more is that for a higher dimension, it may happen that the bound that you can get for Pekin in a higher dimension is not a linear programming bound. So you can actually get some bounds that are not consequences of linear programming bounds using this approach. So let me try to explain one of such bounds. So I'm going to talk about d plus 2 points in dimension d. And this is a result that somehow squeezed in the literature as the Rankin bound. Although Rankin writes in his paper directly that it was already proven by Davenport and Irish. So the result claims that if you have the restricted set of distances from they're all negative, all scalar products are negative, then the number of points is no greater than d plus 1. Or in other words, if you have d plus 2 vectors, you should have an angle that is no greater than 90 degrees. This result is not a consequence of linear programming bounds. So I'll give you a proof of this. There is a very nice, very short proof here. I learned this proof from Math Overflow. I don't know who was the first one to came up with this connection. I think it was on Math Overflow. It was Pablo Soberon who wrote, at least in these terms, the proof. So I'm going to use the theorem of Radon. Again, this is what we proved. I would like to prove that if you have d plus 2 unit vectors, then for 2 of them, the angle is no greater than 90 degrees. Well, we use this very, very classic result of Radon that for any d plus 2 points, you can separate this d plus 2 into two sets whose convex hulls intersect. So the convex hull will have a common point. Well, it's also a fairly short and fairly easy theorem. You can prove it by linear algebra. So this is how we're going to prove the Davenport-Hash bound. We have d plus 2 points on a unit sphere. We use the theorem of Radon. We separate them into two sets, and their convex hulls intersect. Then this common point of the convex hulls, it can be written as a positive combination from one convex hull and positive combination from the other convex hull. And if all pairwise scalar products are negative, then if you write V here as a positive combination from one convex hull and V here from the positive combination of the other convex hull, then all scalar products are going to be negative. So we're going to have a positive combination of negative numbers. It must be less than 0, which is clearly a contradiction. So an extremely nice, very short proof of this bound by Davenport and Hash. By the way, it works for packing points in a unit ball as well. It's still going to work the same, and it gives us quite a lot of information about the set where the angle, the minimal angle is precisely 90 degrees, which is probably not an important word for our situation. Well, so why don't we use our approach, our tool, and combine it with this Hash and Davenport bound? So if we can find a linear combination of Gegenbauers so that it's mapped to a negative interval, then the number of points is no greater than the dimension where we map plus 1, because that's exactly what the Davenport-Hash bound is. And the Conway-Hardin-Sloan orthopex bound is maybe obtained precisely this way. So I'm reformulating it a little. So it's formulated in slightly different terms in their paper and typically applied differently. But if all the distances are from -1 over square root of d to 1 over square root of d, essentially that's a projective packing, packing of lines that we have here. Then the number of points is no greater than d plus 1. So how can we do it? Well, just take the Gegenbauer polynomial degree 2. So this is what we get. The dimension of the corresponding harmonic space is d plus 1 choose 2 minus 1. So just using this bound, we get precisely what we want. The bound is sharp in a sense that if you have more points, then scalar products may be in the closed interval from -1 over square root of d to 1 over square root. So there are a bunch of known configurations that satisfy this condition where the interval is closed. Okay, so these are two well-known bounds that you can get using our approach. Well, can we get something new? So let me show you a couple of bounds that seems to be new. They seem to be new. As far as I understand, they're not sharp though. But still, they're nice explicit bounds that you can get this way. So I was trying to use the same approach, trying to map everything to negative numbers. But now instead of packing lines, I'm going to use packing on the sphere. So if all scalar products are less than 1 over d, then the number of points is not greater than d times d plus 3 over 2. The bound is sharp, though, I think for dimension 2 only. So what do we get here? Well, we just need to carefully choose the polynomial. In this case, we can choose the polynomial so that it vanishes at -1 and 1 over d. Now, this wouldn't give the result precisely because it's 0 at -1, and we would like to avoid 0 as a possible scalar product. So we need to perturb it a little to make it work. And after the perturbation, you can get that the total number of points is no greater than h plus 1. And h here is the sum of dimensions of these two harmonic spaces. So by the way, essentially how can you get this bound? If you assume that the polynomial to use is the polynomial of degree 2, you can actually optimize over this right end of the interval, and this is what I do. So this is the optimal value you can get this with. Well, so this is one bound, and then you can actually optimize for polynomials of degree 3 as well. So if you do that, this is the bound that you get. So yeah, it's obtained in a similar manner. We just make a search over the polynomials of degree 3 with positive Gegenbauer expansions, and we use this Davenport and Hayes bound. So it appears that the best polynomial you can choose here looks like this. It's actually a very nice polynomial because the roots are -1 over square root of d and 1 square root of d. Since it's 0 at -1 over square root of d, you still have to perturb it a little for it to prove the bound. But you can do that, and then just using our general result, it means that the number of points is no greater than the total dimension here, which is the sum of dimensions of 3 harmonic spaces. And this is precisely d times d plus 1 times d plus 5 over 6. Again, I wasn't able to find the situations when the bound is sharp apart from dimension 2. So for dimension 2, you would get here 1 over square root of 2, which is cosine of 45 degrees. And here the number is going to be 7, which is exactly what you should get. Okay. So I was trying to find the bounds explicitly. Very well may happen that if you try to do it numerically, then you can get some new and nice bounds this way, but I haven't tried to do so yet. So this is something to do in the future. All right. So that's one example where our tool may be useful. The other approach is to minimize energy. So let's talk a little about energy minimization problems. So standard definition here is you have a set in dimension d, a spherical set, and you have a certain potential function f. So for a set, you can define the total energy of this associated with this potential function by just summing up the values of f at all pairwise scalar products. And the main goal for us is to minimize this energy of a configuration. So we're interested in the minimal energy in dimension d for endpoints for a potential f. So can we somehow use our tool here? Sure. So if we have a positive combination of Gegenbauer polynomials, we can map there, and then the configuration that we get in the higher dimension using our map should not have an energy smaller than the minimal possible configuration in the higher dimension. So well, that's essentially proof. If you look at the minimizing set in a smaller dimension, you map it to a higher dimension, and then the energy associated with this with the image is at least the minimal energy in the higher dimension. So that's a clear inequality that you can get here. Okay, so I'm going to show one example where you can actually get something from this. So this is one of our recent results with Josiah Park. So what we get here, we studied p-frame potentials And we actually showed that the p-frame energy for the number of points, which is no greater than twice the dimension, is attained on the repeated orthonormal basis. So it's actually a fairly well, there are other situations where your energy may be attained on a repeated orthonormal basis. There's an open problem of phase thought regarding the angles between lines, where you would expect something like that as well. We proved it only for the case when the number of points is no greater than twice the dimension, and as you can see, the degree is also fairly restricted. So the conjecture that Josiah made a year or something ago is that this is true for any number of points, and the power that where this holds should actually be close to 2 when n grows. So this is the conjecture that we don't know how to prove it. Well, why don't we take this result? So that's the result for repeated orthonormal basis. And why don't we try to use our approach here? All right, so if we were able to get the repeated orthonormal basis for this number, for this potential, for f, right here, then we're going to get some results in the smaller dimension as well. So we're going to get some bounds in the smaller dimension. So let's try to do that. And this is one result that where this works. So if you define your potential this way, d plus 1 over d to the power p, then minimizers are going to be repeated regular simplices. So what happens here? You take this function, you look at the mapping in a higher dimension. So your suspected minimizer, which is a regular simplex, it's going to be mapped to an orthonormal basis there. So we can clearly use our general approach and the result for orthonormal basis. And in particular, for any number of points from d plus 1 to d plus 2, the minimizers are going to be repeated regular simplices for this particular potential. This is f of p, right? Multiplied by a constant there, just to make it look nicer. Well, you can do the same for potentials of this kind. So what happens here? The potential is d squared minus alpha squared, and the bound is going to be sharp for the maximal set of equiangular lines, which exists in a bunch of dimensions, and in a handful of dimensions actually, not so many, but exists in some cases. The proof is fairly straightforward as well. This is the polynomial we take. If alpha squared is less than 1 over d, then it's a positive combination of Gegenbauer polynomials. So it's a Gegenbauer polynomial of degree 2 plus a constant. And the dimension that you get this way is precisely what you want. It's going to be d plus 1 shifted. So it's one more result you can get this way. Yeah, hopefully it's convincing as well. So take something nice in a smaller dimension that you suspect must be a minimizer, map it to a higher dimension so that it's an orthonormal basis, and then use the result for orthonormal basis. By the way, if the conjecture of Josiah for orthonormal basis is correct, then all these results are going to be extended as well for any number of points. Right, so we're going to have repeated regular simplices here, repeated maximal equiangular sets there. It's just going to work the same. So the bottom line here, we should work with orthonormal basis. This is the key object here. Okay, so that was my second convincing argument that this is what we should study. The third direction where we can use our tool is to construct new configurations. So So Bondarenko, some number of years ago, noticed that if you take minimal vectors of the E8 lattice and you apply the second Gegenbauer polynomial, you apply the map phi2 here, then very nicely, all the vectors that you get in dimension 35 will have scalar products plus minus 1/7. This is a nice set that you get this way. I wouldn't say it was new, because you clearly can associate a strongly regular graph to minimal vectors of E8, and it's just going to be a spherical embedding of a strongly regular graph in dimension 35. But still, it was a nice find that you can get E8, and using this mapping, you can get a nice set in dimension 35. And of course, it's an optimal packing of lines as well. And a couple more papers in this direction were done by Miyazaki, who studied essentially the same mapping, phi2. So he took a bunch of sharp configurations. He looked at what you get after you map them, and he got fairly nice sets as well. So let's try to study what's happening here. So is there any general way of getting nice configurations using the mapping that we have? So in order to study that, we have to learn what nice configurations are. So what we mean nice? What do we want to get out of this mapping? So I would like to define spherical designs for that. And so spherical design is a finite set of points, so that when you integrate all polynomials of degree no greater than t over the sphere, you get the same as if you average over this finite set of points. So there are all nice sets you may think about are essentially spherical designs for some strength T. Well, if you look at this condition only for homogeneous polynomials of degree 2, then the set that you get this way is called in literature a tight frame. Well, it's everything is unit norm, so I omit these words. It's a unit norm time frame, of course. And tight frames are essentially antipodal 3 designs. So for a tight frame, if you for each point, if you add the opposite point and you look at this set, that's going to be an antipodal 3 design, because of the opposite vectors, the condition will work for degree 1 and 3 as well, and they also may be called projective 1 designs. Okay. So here's a new result in this direction. It appears that if you take a 2K design and you use our mapping to the space of spherical harmonics, you always get a tight frame. The degree of the polynomial should be no greater than K though. So this was noticed by Miyazaki for K equal to 2, essentially. But it works for all of them. It works for any power. So what is the proof? I'm gonna give a sketch of the proof. Well, for a tight frame, you have a condition to check. If the average square of the scalar product is 1 over d, 1 over dimension, then this is a tight frame. The inequality was found by Sidelnikov. Then Vankov found that this is a criterion for being an antipodal 3 design. In his paper, it was about designs. And a more recent paper of Benedette and Ficus showed that even the local minimizers of this satisfy the condition and produce tight frames. So what do we need to do? We just need to check this tight frame condition. So let's look at it. After our mapping, all scalar products are the values of the Gegenbauer polynomial. And since it was the design at the beginning, instead of looking at the sum, we can actually look at the integral of the Gegenbauer polynomial with respect to the normalized Lebesgue measure. And this is something we can find. It's actually, it follows from the definition of zonal spherical functions of Gegenbauer polynomials. So that's essentially the whole proof. Well, so we got that Gegenbauer polynomials, these mappings are fine, right? Well, maybe our general mapping, which is a combination, positive combination of these mappings, will work as well. So let's try to do it. Let's take a positive combination of Gegenbauers, and let's try to check the value. The setup is the same. We have 2K design at the beginning. The degrees are from 1 to K of Gegenbauer polynomials. We check our condition. Synthetic design, it's the same as to integrate on the sphere. And if you look at the square of this value, then the product of Gegenbauers of different degrees are going to give us 0, because it's an orthogonal system of polynomials, essentially. So that's going to give us 0. And for each of them in particular, we're going to get the value of alpha squared, the coefficient squared, over the dimension of the space of spherical harmonics. So we get this value for the integral. And then at this point, I'm using Cauchy-Schwarz. So this is at least the sum of values in the numerators squared over the sum of values in the denominators. And this is 1 over h. This is exactly what you should get. Well, if you check carefully the condition, when does the Cauchy-Schwarz hold? It means that alphas must be necessarily the dimensions h over the total dimension of the set we get at the end. So the answer is yes, you can get tight frames this way, but the coefficients are essentially prescribed. You don't have a choice in the coefficients. They're essentially prescribed, they're defined by the degrees. And this is the theorem that you can get this way. So it's a more general result. So you can start with any 2K design. You can choose any subset of degrees for this 2K design. You can produce a new tight frame in a higher dimension. Okay. So that was my convincing argument number 3, that this is actually a nice map. So using this map, we can start with nice configurations with smaller dimensions and get, well, not that nice configurations. Tight frames are arguably not that nice as 2K designs, obviously, but still very nice configurations in higher dimensions. All right, and for the last part of my talk, I would like to show the a short proof of the Kiesel number problem in dimension 3, which I essentially stumbled upon when I was working on this topic. It's not directly based on the mapping to the space of spherical harmonics, but it's fairly nice, and hopefully I can explain it in 5 minutes too. So we would like to show that the Kiesel number is not greater than 12 in dimension 3. And this is the polynomial that I found. It doesn't look very exciting, I guess. So let me try to explain to you how we can use this polynomial and prove the bound. So first, this is the key lemma that we're going to use. Yeah, by the way, before I go into the proof, the approach is fairly similar to the approach of Musin, because on top of his proof for the Kiesel number problem in dimension 4, he also found a new proof in dimension 3. But the polynomial is much nicer in the sense that it allows us to get rid of a lot of cases in the case analysis. So the proof is really just a one-page proof. All right. So if we can show that for any point in our set, the sum of values of a polynomial, of this polynomial P, at scalar products with this point x is not greater than 1.23, then I claim we can actually solve the Kiesel number problem. And here's the explanation. So let's say we have a set with n points, then summing up all these inequalities for all n, we're going to get that this total sum is no greater than 1.23n. On the other hand, if we sum up all the values of this polynomial at all pairs of points, then for all eigenvectors, the sum is going to be non-negative. And for this constant, it's going to be at least this constant times n squared. So we get that the sum is no greater than 1.23n, and at least this nice number times n squared. So dividing one by the other, we get 12.994. And this is the reason why the polynomial is not that nice. Actually, it's really that close. I can modify it a little by taking a different constant here. If you optimize with respect to a constant, you probably would get something slightly better than that, but not much. Something like 12.97, I guess. Okay, so we're left with this lemma. We would like to prove this lemma. So again, we have a set of points. All scalar products are no greater than 1/2. We would like to show that the values of this polynomial at scalar products is no greater than 1.23 for a given point x. Okay, so this is the lemma we would like to prove. Well, what is good about this polynomial, and this is one of the conditions that I put when trying to find it, when optimizing, is that it's negative from -1/square root of 2 to 1/2. So whatever points we have that have this scalar product with x, they're going to give only a negative contribution to the sum. Well, how many points can give a positive contribution? They all should lie in the spherical cap with the center -x and the radius pi/4, because this is exactly what you get for the scalar product -1/square root. And it appears that if you take a square on the boundary of the spherical cap, then the distances are exactly pi/3. So no more than 3 points can be in this cap. And this is actually very nice. So now we have just a bunch of cases. So we have a case when there is exactly 1 point. So we have a case where there are 2 points. We have a case where there are 3 points. We're kind of got rid of all the combinatorics here, essentially, almost all the combinatorics here. So what if there's exactly 1 point there? Well, clearly we can just look at the maximum of the function, and it's less than 0.23. So for 1 point, that's easy. We have 2 more cases to tackle. What if we have 2 points? Well, let's try to maximize the sum. If you want to maximize, it appears that the best situation is when the distance is exactly pi/3, no greater than that, between these 2 points, and -x lies between them. So it's a 1 parametric family of configurations actually for these 2 points y and z. We can write the values explicitly. So if one scalar product is t, then the other can do it in this way, just explicitly found. And then we can check polynomial inequality that you get this way. You check it, and it's no greater than 1.23 as well. And case number 3, it's a little more complicated. Instead of 2 lines, it's essentially a paragraph for the proof. So we have 3 points. Carefully moving the points, we can reach the situation when the angular distances between these 3 points are exactly pi/3. Then we're going to have this triangle. We're going to rotate it with respect to the point that is furthest from x. And we can do that increasing the sum. It's fairly easy to show. Then the rotation is going to stop in 2 cases. So one is when you rotate the triangle and 1 point reaches the boundary of the cap. But then we lose this point, because if it reaches the boundary, the value of this point becomes negative. And we need to take into account only 2 points. And the other situation is when the second point becomes the point on the same distance from x. So we're going to have 2 points furthest from x on the same distance. And the third point, it's again a one-dimensional, a 1 parametric family of configurations. So we say that this is t. This distance, the scalar product is t. We find the third scalar product using t, and we get the polynomial inequality that we can easily check that it holds as well. Now, where is this polynomial coming from? Essentially, I took all the conditions needed here, starting from the fact that it's negative on the interval from -1 over square root of 2 to 1 to 1/2. And we also need the value at -1, of course, to be smaller than 0.23. And we need, at one point, we also need the convexity. When we move the triangle, we need the convexity in some interval. So if you take all these polynomial inequalities, and of course these polynomial inequalities, those that we get at the end, if you take all these polynomial inequalities, and you solve the optimization problem, taking these polynomial inequalities into account, then this is what you get. I fixed the value 1.23. You can actually optimize by this value as well. It's going to be a little, as I said, it's going to be a little better, but more or less the same value that you get at the end. So that's my short proof of the Kisa number problem in dimension 3. And I guess that's it for my talk. Thank you.
Thank you, Alexey, for a lot of nice results. So are there any questions or comments from the audience? So there was some discussion in the chat about the results about p-frame energies. So about extending them to 0. So for p going down to 0. And I think Josiah and Castro commented that you could probably extend downwards as well.
Yeah, probably everything that happens for p equal to 1 should be extended to p equal to 0. At least when you expect the orthonormal basis to be your minimizer, then surely it's going to be extended to 0 as well. And since we map to orthonormal basis, it should work. Yeah.
Carlos, yes, please.
Your result. Oh, sorry.
Hi there. Well, very nice talk. So maybe you mentioned something about this, but very briefly at the beginning. Let me connect my video. So you said all the time about real harmonics, but say for the 2-sphere, you also could have complex harmonics, I guess, right?
Yeah.
Maybe, does it give you something new? Did you try or someone try?
I haven't really tried it. So it is very much work in progress. For instance, the paper of Bondarenko, I found it a week ago. So this is something very new. I haven't really tried it in other spaces. I guess it should work. I'm pretty sure a bunch of energy minimization results should work for SIG problems as well. That just should hold. But I haven't had time to check it. And maybe a bunch of results are going to work for finite 2-point homogeneous spaces as well. Hamming cube. I guess a bunch of stuff should work, but I'm not really sure what exactly.
Yes, sir. Okay, thank you.
Alexey, very good talk. Could you go back to the result where you were somehow like pushing like a tight frame using this polynomial to different space?
This one?
Yes, thank you.
Uh-huh.
All right, thank you. I see. Thank you. Will the presentation be available to see? Like, do you have a PDF of it that we can get?
I think it's there. I think Alex.
Oh, yes. Sorry, I see it now. I see it.
Yeah, the slides. Yep.
Mm-hmm. Thank you. I see it. Thank you.
Yeah, for this particular part, I don't even have a write-up because again, I stumbled upon this upon these configurations in higher dimensional spaces when preparing for the talk.
I see.
right at the end of your talk, you were giving a proof method for the kissing number in dimension 3, right?
Yeah.
How well does that methodology translate to other dimensions?
So Musin's proof for dimension 4 is more or less along the same lines, where you find a nice polynomial and you prove this this kind of lemma. But as a matter of fact, the situation becomes worse and worse the higher you get. So here we were kind of lucky that we can restrict our number of points to 3. I think it's impossible to find a polynomial for the 4-dimensional problem where you can restrict to 3 or even 4 points. So you would have to work on the case analysis for a bunch of points in this spherical cap, and it's fairly tedious and annoying. If you read Musin's paper, you will actually see it. And I don't think it's possible in dimension 5. At least I don't see how it can be done. Maybe if you couple it with some other argument, maybe it's gonna work. I don't see it.
And for dimensions 8 and 24?
Oh well, you don't need to do that in dimensions 8 and 24. It's,
sure.
Because you can make the values no greater than 0, no greater than is. I mean, it already works for dimensions 8 and 24. It's an extension of the Del-Start method. So whatever you get by the Del-Start method is sort of included in this method as well.
Okay.
So I think this paper of Bondarenko, Radchenko, and Razovska, they do something maybe morally equivalent, where they also look at embeddings of configurations into the spaces of spherical harmonics, right? And then they optimize on the space of polynomials.
I'm not sure it's directly connected. So, but the reasons I haven't said that, but we can get tight frames by using these methods. I think we cannot get polynomial. We cannot get designs of higher strength than what you get for tight frames using this mapping, because essentially this the subvariety that you get by this mapping, I think it's not a design of higher strength itself, the subvariety itself.
Mm-hmm. Okay, so it's not.
So this is kind of the reason. So what happens here if you have this the subvariety, if it's a 2 design itself, and you get a design within that, then it makes sense that you get a 2 design at the end, a tight frame at the end. But if it's not a design of higher order, then it shouldn't work. I mean, it's just my suspicion. I'm not entirely sure.
Is the problem that you have like the 0 mean condition not holding? Like, are you saying that you could only get like a projective design, but you wouldn't be able to sort of knock out the odd coefficients? Or are you saying it's something more than that?
I'm just using the projected design condition. Yeah, I'm not. I don't think you can get the 0 mean.
Okay. Thanks.
Okay, are there any more questions, comments? So if not, let me first disable the recording. So I